Okay, before we go on to some maybe some slightly more subtle properties, I want to say, okay, these three properties represent things that we know are going to happen if we're adding vectors in R2. Yeah, I'm going to tell you the same thing happens if you add polynomials in X. I'm going to write up real coefficients. Polynomials with real coefficients in X, real number coefficients. You can have polynomials that have imaginary coefficients or complex number coefficients. But we're sticking with real numbers for the moment, okay? So if you have real number coefficients, polynomials with real number coefficients, polynomials in X, where X is just your variable, well, what are examples? First of all, what do we mean by polynomials in X? Well, x squared plus 5x minus 3, x cubed plus 7x squared minus 9, quantity x minus 7 raised to the 53rd power. Every one of these, and of course we'd have to expand this to see just what it is, but we know that when we do this, we're going to get a sum of multiples of non-negative powers of x. Okay? Like negative 3 is negative 3 times x to the 0, right? 0 is not negative. 0 is a non-negative power of x. Now, I didn't say it right. Non-negative integer powers, and of course 0 is a non-negative integer. Okay, it's not a positive integer, but it's not it's a non-negative integer. And then the next power of x on the integers would be x to the 1, which is just x. So that's 5x to the 1. That's a multiple of a positive integer power of x. Wanted to make sure I said it right. X squared, it's a multiple of x raised to the 2. 2 is a positive integer, and so forth. We can't have a square root of x. That would be like x to the 0.5, and 0.5 is not an integer. It's positive, but it's not an integer. We can't have 1 over x squared. That would be x to the negative 2. That's not a positive integer power of x. So, polynomials, sums of positive integer powers of x. Okay? Now, if we add one polynomial to another, do we get a polynomial? Well, yeah. For example, if I add this to this, let's see, I don't have an x cubed up here, so I'll just have x cubed. Now I have an x squared and a 7x squared, which gives me an 8x squared. And I'll observe it doesn't matter if we do 7x squared plus x squared or x squared plus 7x squared, commutativity. We're going to get an 8x squared. We're going to get a 5x, there's no x term down here. We're going to get negative 12, x to the 0, or just negative 12. So if we add these, we get this. We still get positive integer powers of x. We can't get a power of x that's not a positive integer by adding positive integer powers of x. Okay? And you think about why that's true. I think I just said something that's kind of circular. Okay, so clearly this example shows that if we add two polynomials we get another, but we got to figure out how to write that out. Okay, so we know it's going to be true. You know, we know if we think about it a little bit it can't be otherwise, but how would we write out a proof of this statement? Okay, what about commutativity? Okay, well, we know it's true because we know it doesn't matter in what order we add two polynomials. We're going to get the same thing. We've been doing that, you know, ever since Algebra 1. But how do we write it out? Okay, we're going to leave that question, but it is true. Associativity. If I've got three polynomials and add the first to the second, and then do whatever I get plus the third, it's the same as I take the first plus whatever I get when I add the second and the third. And again, we're just adding coefficients of like powers. And the coefficients of like powers are real numbers. So we're just essentially adding real numbers for every power of x. And we inherit the properties of closure, which is when we add two and get another, commutativity and associativity from the closure of real numbers. If we add two real numbers, we get a real number. And from the commutative and associative properties of real numbers. They're inherited in a way that's pretty easy to, relatively easy, very easy to understand, and relatively easy to write down. Okay? Now, what about 2 by 2 matrices over reals? Meaning 2 by 2 matrices, you know, two rows, 2 columns, 4 numbers, and they're all real numbers. Well, clearly, if I add this to this, the number in each different row column adds to the number in the same row column of the other matrix, so I'm just adding 2 real numbers in each case. If I add them in opposite order, as I would if I, instead of doing this matrix plus this one, I do this matrix plus this one, I get the same thing in whichever order. So we again inherit commutativity. And in a similar manner, we inherit associativity. It's easy to understand that we do, it's easy to see that we do, it's easy to really believe that we do, but it's a little tricky to write down exactly why that's the case. And we'll be working on that in our next class, but we want to get these properties down so that we know how to test various sets to see if they're vector spaces, okay? Now, it's going to turn out that all the properties we list for vectors in R2, the properties that we choose to characterize a vector space, are satisfied by real valued polynomials in X, okay? And if you extend the reals to complex numbers, it would be complex polynomials in X, okay, where you have complex coefficients. Don't worry about that. We're not going to do that anytime soon. Or 2 by 2 matrices over real numbers. They satisfy exactly the same properties that we think characterize our work with vectors in R2. So we're going to go on to a couple more properties. Now there are 10 properties. We've covered 6 of them, and the last 4 are pretty easy. Actually, these 3 are probably the ones that would give you the most trouble. So we wanted to get these 3. The last 4, once you get the gist of the first 6, the last 4 are not difficult.